Okay, so that's an extra. So that's just more for curiosity, for people that like a little bit more of math. So that would require a little knowledge, a little bit of knowledge in calculus 1, because they're going to be doing derivatives, and also linear algebra, because they're going to be doing matrix notation and calculation with matrices in this one. And that's a presentation that I did a while ago for the cruise Tech Talks that we have every Friday. And the idea was to talk about what is backpropagation. And to understand what is backpropagation, so I'm going to be talking about the fully connected neural networks, not the convolutional ones that we did. We need to understand what are each one of those parts of a neural network. What is a perceptron? That's also called a neuron. What is the forward propagation? That's the part that we are doing the predictions, even though they might be wrong for the weights that we have. And then that's going to allow us to do the back propagation to update our weights in there, and just some final notes. So talking about the perceptron, the neural networks, again, it's based on our brain's neurons. So we're going to see a lot of images similar because I copy and paste some of those images. So I can go quickly in this part. So this is a fully connected neural network where you have the input layer, hidden layers, and output layer. A deep learning is any neural network that has 2 or more hidden layers. That's the definition of deep learning. And each one of those circles in here is called a perceptron or a neuron, because it's based on the neurons that we have in our brain. But there is a math inside each one of those perceptrons, and that's the same of the equation of a line initially. So remember that I told you that for each one of those neurons, we're going to be receiving the information from the previous layer, from the neurons of the previous layer. That could be the input layer, or could be the previous hidden layer. We're going to be multiplying this feature here, or this information here, by a weight, and summing to this one multiplied by another weight, and summing this one multiplied by another weight. And that comes to this kind of a draw in here. We're going to start to have an equation of a line. And not only the inputs, we still have to include a bias. So basically, this is the equation of a line in here. Right? We have the intercept, that's the bias, and our features or our outputs from the previous layers multiplied by those weights, the equation of a line. So to make this not necessarily a linear model in here, we have to apply something called an activation function. So the first activation function that was proposed in the literature was a step function. So everything that was negative was 0, and everything that was positive was 1. To make this linear, strictly linear function a non-linear function. And that's how we are going to start to have those mathematical representations. So that's the equation of the line. That's going to be the sum of all the features multiplied by the weights plus the bias. And here, after we apply some activation function, not necessarily a step function, I'm just calling this uppercase omega, and an operator applied to this line equation. So this one is a non-linear equation anymore. And there are different activation functions. And visually speaking, the most common one is the ReLU, where we have negative numbers gonna be 0, and the positives are gonna be themselves. There is a reason for that. The first one, it works quite nicely. Second, for the computer, it's way faster to do the calculations, because when the number is negative, you just say it's 0. And when the number is positive, you just say that it is itself. So there are not a lot of calculations during this activation function. And that's going to be applying for each neuron that we have in our neural network. Another very common one is the sigmoid, and that's the one that you're going to be using as an example today in the equations. Basically, that's the same of a logistic regression, if you think, where we have here the probabilities of zeros and ones, basically. We have the tangent hyperbolic, we have the Lickey-Billou, max out, we have different activation functions. Probably the most common one is the ReLU, followed by the sigmoid. Then we have to talk about the forward propagation. So that's when we start to do our predictions. We're going to start with those weights that we have there with some kind of a random weights. And the forward propagation is basically, we start, again, with some kind of a random weights, and we calculate our predictions in the end. And that is our equation for the forward propagation, actually. Now that comes a little bit to matrix equation and linear algebra. And when we start to do those matrix notations, because in the backpropagation, things are going to start to make more sense. You're going to see that you're going to start with this huge complex math. In the end, it's just going to be a multiplication of terms that you calculate quite quickly inside the neural network. So that's how our layers are represented. So we have some layer in here, could be a hidden layer, could be an input layer, our current layer, and the next layer. So for each one of those neurons, we have the equation of a line and an activation function being applied to them. So for one layer, for the whole layer, not for only one perceptron, for your whole layer, and actually for your whole network, that's how you could represent this equation for this layer. That could be an activation function of a matrix of weights. That would be all those weights that you have here. That comes from different outputs from the previous layers going to different neurons of your current layer, times your outputs of your previous layers. That's going to be those x's, plus the biases that you have in each one of them. So that is the matrix notation that we are using in here. I know that's going to start to look like a lot. So when you're working with matrix notation in math, we have these bold letters. We have this W bold, X bold, and B bold, meaning they are matrices or vectors. And actually, there is an equation in the end for us to calculate a prediction. If you wanted to calculate what is the predicted value, what is our probability, or if you're doing classification, or a value, if you're doing regression, how do we go from the first layer to the last one, mathematically speaking? So we're going to be using this terminology. We're going to have our input data in here. Those are our features, X, and this one here denotes the layer they are in. So that's from the input layer. Going to the first hidden layer, actually, with the weights from the first hidden multiplied by the weight by the first hidden layers plus the bias of the first hidden layer, and then apply an activation function. And all this information here on this first layer, that would be this one, is going to be now, all this output here, all this equation, is going to be the input for the next layer. So this one is going to be multiplied by the weight for the second layer, plus the bias of the second layers. and applied the activation functions of the second layer. And again, this one's going to be sent to the next layer, and so on and so on. And that's the equation of a forward propagation. That's how we calculate our predictions. It's just a straightforward math, basically. And then, knowing that, we can go for the backpropagation. And that's going to be a little bit more painful part, because that's going to be a little bit more mathematical heavy. And what do we do in deep learning? We do the forward propagation. We calculate our loss function. Now that we can calculate the predictions by having our initial weights, we know how much mistake we did. And then we have to update those weights to try to minimize for those errors. And we do that iteratively. We do a forward propagation, back propagation, and then we do a forward propagation again, see the new errors, and a back propagation. And keep doing that until we get some convergence that we want. And now we have to just remind a few things that we have to remember. What is our loss function that you're going to be using? Let's say we are doing regression. So we're going to say that our loss function is just going to be the mean squared error. So basically, those are going to be the square of the residuals divided by the number of data that we have. And remembering that this is the true value that we have for one row, and that's our prediction. And remember from the forward propagation that our prediction follow this equation. And from calculus 1, you're going to be using the chain rule of derivatives. If you wanted to calculate the derivative of f relative to x, knowing that you have those chain functions in here, we have to use the chain rule. So the derivative of f relative to the x is going to be the derivative of f relates to j, derivative of j related to h, derivative of h relative to the x, each one of those derivatives multiplying each other. And we're going to see how we're going to be using that. So let's start with a very simple example. Let's say that's our neural network. We have one input layer, two hidden layers, and our output layer in here somehow. So let's take a look in what we have in this specific neuron down here. And that's what we have. From this specific neuron, you're going to have an output that's going to be our predictions. Y1, 4. Y1, meaning that's going to be the predictions of the first neuron in here. And the 4, meaning that we are in the layer 4. The cost function is the mean squared error that has this also notation. That's also the L2 norm notation. So that's how now we're going to connect this prediction to this cost function. So that's what we are typing in here. How this prediction, that's the output of the layer 4 for the first neuron, is connected to the cost function. Now, what do we have in here? This prediction is actually the activation function of something that's calculated inside this neuron, the Z1 of the layer 4. And for this example, we're going to be using the sigmoid because it's quite simple to calculate the derivative of the sigmoid, just to show how it's simple to do deep learning in the end. So this prediction is basically the sigmoid of whatever we have inside here. And that is the input of this neuron. What is the input of this neuron is the Z1 for. And the input of this neuron is the line equation. So this Z1 is going to be the output of the previous layer from this neuron multiplied by this weight plus the output of this neuron here multiplied by this weight plus a bias that we have here. So this is the equation of a line. So that's how we're going to now connect those weights, because the weights are the only things that you can change inside a neural network. You cannot change the input parameter or the true values. So now that's the path that we have to connect our weights to our cost function. And that's the part that you're going to be using the chain rule. We wanted to take the derivative of the cost function relative to those weights, because you want to optimize for those weights. Now let's take the example and try to optimize for this specific weight here. Let's see all the equations that are going to come from this. We're going to have this chain rule now. To optimize this weight here, the cost function relative to this weight, we have to calculate the derivative of the cost function relative to this weight. By using the chain rule, it's going to be the derivative of the cost function related to the y14, and we have the equation that connects both. The derivative of y14 to z14, and we have the equation that connects them both with the sigmoid, and the derivative of z14 relative to the weight 11 in here. So now, calculating a few of those derivatives, the derivative of the LT norm is going to be twice of the residual. That's the derivative of this first function. And the sigma prime, we're just going to be denoting sigma prime as the derivative of the sigmoid. And we're going to be showing later what is the derivative of the sigmoid. And then we're just going to start to replace them down here. And the next part, now we need to derive the Z14 related to this omega 114. And that's quite simple because we are summing this, summing this, summing this. So the derivative of this summation is basically the summation of the derivatives. So the derivative of this part relative to the omega 11 is 0, to this second part is 0, and to this part is just going to be y13. It's just going to be the output from the previous layer. And then you can just replace it in there. Now, let's calculate what is the derivative of the sigmoid. So the derivative of the sigmoid, when you do some calculus, you're going to see that's the sigmoid times 1 minus the sigmoid. That's when you use calculus 1 to calculate the derivative. So basically, if our sigmoid is called A, in our case, it's going to be the y14. So it's going to be y14, 1 minus y14. If you replace here now, you're going to see now that this derivative that look like to be scary in the beginning are just a multiplication of terms that we calculated already. So we have this calculated, we have this calculated, and they're just multiplying and subtracting them from each other. And we have the true value of y1 in here. So that's how things start to become simple. Look like to be quite complex. Now it starts to become simple. And only to make it a little bit simpler for us, we're going to call this part as delta, because that's one of the notations they use for deep learning. Because that's everything that's related to the layer 4. We have the outputs of the layer 4 and the true value. So everything that's related to the layer 4, we're going to be calling a delta. And that's it. So that's how we update, we calculate, not update, we are calculating the gradient in this one, the derivative. We are calculating a gradient for the omega 11 in here. Now, if you do for the other weights and for the biases, you're going to have this equation. They're going to be very similar. You're going to use exactly the same deltas. The difference for this second weight here is going to be multiplying by this output. And for the bias, you're just going to be multiplying by 1. It's just going to be the delta. Now, what we need to do, we need to figure out the deltas for all the previous layers that we have. We know what is the derivative of the last layer. Now we need to figure out all the deltas. And also using the chain rule, we see that that's how we calculate the deltas, basically. The delta for one layer in here is going to be the delta of the next layer. It's going to be a function of the delta of the next layer. So that's why it's called a backpropagation, because to calculate the delta, for example, for the layer 3, we need to know the delta of the layer 4 first. So that's why it's called backpropagation. This is a mathematical solution. So by knowing the deltas of the layer 4, we can calculate the deltas of the layer 3. And now knowing the deltas of the layer 3, we can calculate the deltas of the layer 2. And basically, those are the equations that we need to do the optimization. We know how to compute the gradients now. Those derivatives are called the gradients. That's when you're going to be doing the optimization. And how to calculate those gradients is just depending on those deltas. That is just multiplication of terms that you calculated since in our forward propagation. So it's quite straightforward to calculate it.